For this capstone project, our team was tasked with upgrading a tracking gimbal for aerial demonstrations, sponsored by Lockheed Martin. Here's our team. Our majors cover several disciplines, and this became one of our greatest strengths. The first portion of this video will focus on the software and mechanical upgrades we made to the gimbal from the previous semester, starting with our team's lead software engineer, Charles Casey.
On the software side of this project, we use Python and various libraries to optimize our motor software and implement a terminal-based user interface for anything that the user might want to control on the gimbal. Initially, we were given a set of PID gains for our motors that were not specified for any specific use. So for our project, we took these through a series of 7 iterative steps to find a balance of these gains that would optimize current usage, rise time, overshoot, tracking amplitude, and phase lag. We also implemented a user interface where anybody can use our gimbal however they so please. So the way that it works is the user is prompted to calibrate the hard stops and then brought to the main dashboard. From there, they can choose between Xbox mode, GPS mode, change some settings, or view the debug or the logs.
Next, we have the team's lead mechanical engineer, Edward Kelly, describing the upgrades he made to the electrical box, gearing system, and side box.
Alright, this is our upgraded tracking gimbal. In the front, we have a fuse box, which ensures electrical safety. We have our I/O ports. On the back end, we have a power entry module, which powers this device in one cable. On the side, we have our tilt box, which houses the other O drive and other electronic components and the antenna. From here, we have quick release cables, which allows us to take the camera off in one go. And then here is our upgraded zoom and focus ring. It's easy to take off. We have just little thumb screws and yeah.
The third main upgrade we made to the previous semester's gimbal was implementing an RTK GPS system, which proved to be much more effective than the previous semester's system. Here's our lead computer engineer, Ethan Clemetson, describing the architecture of our RTK GPS system.
So this is the GPS. It operates at 10 Hertz and communicates over long-range radio. In our testing, it has a distance of at least 1,000 feet. And how it works is you have this GPS antenna, which connects to the GPS module, which connects to the transmitter over UART, and then that transmits out of this antenna to the receiver that is over there.
To wrap up, let's look at our field testing results, which demonstrate our ability to successfully track across 3 different cases of increasing complexity. First with walking, then running, then driving. Per sponsor request, we utilize RTK GPS as our primary tracking method, but you can also track manually with an Xbox remote as shown on the right. Based on our comprehensive ground testing and simulation data, our gimbal is primed to maintain a precise lock on any aircraft featured in a Lockheed Martin aerial demonstration, which, after all, was the goal we set out to achieve.